Welcome back. In the previous modules, I was talking about the continuous time systems and how to design sliding mode control for the continuous time systems. So, in this module, I am going to discuss about the discrete time systems, okay, and how one can able to design discrete sliding mode control. So, obviously, whenever we are going to talk about the discrete sliding mode control, one of the crucial things that is the stability of the discrete time system. And once you apply the idea of sliding mode, so most of time our system, even if that is linear, that is converted into non-linear, okay, and due to that reason some rigorous mathematical background is required to handle the non-linear discrete time system. So, in this first module, it means that first lecture of this module, I am going to discuss about the stability concept of the discrete time systems, and then next onward I am going to deal with the discrete sliding mode control. So, purpose of the discussion, obviously I am going to deal with the rigorous stability notion of the discrete time system, because now type of system is going to change here, and due to that reason first I have to again deal with the stability theory. And obviously we are trying to understand the gap between practical implementation as well as the theoretical formulation or foundation, and we are also going to develop the tools for finite time convergence in case of the discrete time system, because we are going to deal with the sliding mode control. And in sliding mode control also, whenever we are going to discuss in discrete framework, so suppose that if the first state is Z1k and second one is Z2k, again idea is exactly the same. We are designing some kind of discrete manifold, and meaning of discrete is that we have something only defined at the discrete point, and what is basic idea, in finite time I have to converge to this manifold, and after that in subsequent instant we have to maintain along this particular manifold. So, again in order to converge in finite number of sequence, I need concept of finite time stability. So, that notion I am also going to discuss in this particular lecture. So, what is key focus? I am going to characterize the stability. So, all notion of stability like Lyapunov stability, after that asymptotic stability, geometrical stability, that new concept basically comes into picture whenever we are dealing with discrete time system, that I am going to discuss, and after that finite time stability we are also going to discuss. One of the main important issue that whenever we are going to talk about the sliding mode control, obviously we are implementing sliding mode control to do something more, that is our plan is to reject matched uncertainty or minimize the unmatched uncertainty, and due to that reason some kind of stability notion in terms of the ISS, input to state stability, that is also required. Okay, so we are going to extend the notion of stability whenever we have some kind of bounded kind of disturbance, and obviously Lyapunov tool is very efficient, either that is the case of linear system, non-linear system, discrete system, hybrid system, stochastic system, everywhere, and due to that reason we are trying to understand the Lyapunov formulation for discrete time non-linear system. And whenever we are designing controller, obviously some kind of criteria which one can able to verify algebraically, that is required. So, using this notion we are trying to understand. Okay, so several practical examples or numerical examples I am going to discuss in this particular lecture. So, whenever we are dealing with the non-linear discrete time system, exactly same like the continuous non-linear system, some kind of function is frequently that is going to appear, that is called comparison function. What is basic idea, either that is continuous time or discrete time, whenever you have higher order system, so in using some mechanism we are somehow converting into first order system, because why we are doing that, suppose that if I have higher order system, then I don't know that what is their convergence behavior. But suppose that if you have higher order system and if you convert into somehow one dimensional system, then now things are very easy, because in one dimension, suppose if you are in this real line, one dimension means nothing but some kind of real line, where it might possible I have continuous point. In case of continuous time system, in discrete time system I have discrete points. So if you are here, so you know that if I have some kind of converging behavior and if this is the equilibrium point, then I will move in this direction. So you have unique direction from here, that only in order to converge here you can just follow this line. In this way also I can able to follow, or either I am going to live here. So whenever I have n dimensional problem, we are trying to convert it into one dimensional problem. And somehow if you see carefully the comparison function or Lyapunov function, so their idea is basically based on this particular philosophy. So during whenever you are going to convert, at that time obviously most of time you are not getting equality. What does it mean? That whatever equivalent system that comes into picture, that is not come in form of the differential equation, that will come in form of differential inequality. Okay, and due to that reason, once differential inequality comes into picture, there are several functions or several comparison kind of function comes into picture, such that I can convert differential inequality into differential equation. Okay. After that, whenever we are formulating some kind of function, and suppose that if I have to converge to 0, so left hand side is unnecessary, and due to that reason we have to show that whatever transformation function I am going to use, that is well defined, that is bounded. So these kind of things, in order to understand these kind of things, some comparison function theory is required. Okay. So another important aspect of comparison theory is that whenever you are dealing with some kind of autonomous system, and whenever you are moving from autonomous to non-autonomous system, it is possible to show that now time is explicitly appear. So now solution trajectory is actually function of the time. So somehow uniformity with respect to initial condition is lost, but still there exist several class of non-autonomous system. Meaning of non-autonomous system is nothing but some kind of system where time is also there and state is also there. Okay. So whenever you are going to solve this class of system, it is possible to show that solution most of time that is depending on the initial time. Now there exists some class of non-autonomous system where solution is uniform with respect to initial time, and at that time it is possible to show the capturing of that function required some special treatment, and in that particular treatment comparison functions are very helpful. Okay, so first I am going to introduce the notion of comparison function, and this is applicable for continuous as well as discrete. So first comparison function is called class K function. So what is meaning of class K function? We are talking about some kind of function alpha, and here whatever argument I am going to give, that is again positive. So and this positive domain of this, assume that domain is 0 and a, and alpha equal to 0, this is 0 we know, and now I have domain from 0 to a, and again that is going to map from some kind of positive side only. So I have some kind of function alpha where domain 0 to a, then that is going to map again some kind of positive function. Okay, and what is property of that? That is continuous and strictly increasing. So if that is the case, we are going to tell that kind of function is class K function. Okay. Now if you increase this, here I have taken a, but obviously I have just single variable, so one can able to assume that is s. Now s is defined between 0 to infinity. Okay. So now as s tending towards infinity, and if this function is also tending towards infinity, then that is called K infinity class function. And if you see carefully that whatever Lyapunov function we are constructing, that is going to satisfy this particular property. Okay. So Due to that reason, I have told you that these class of functions are very useful. It is also possible to show that if you will take some kind of positive symmetric definite matrix Vx, so most of time that is bounded by two k class function. Okay, so alpha 1 and x. So these kind of result you can easily able to see if you explore the Khalil book. That is one of the very standard book. So if you are interested in non-linear system, even if linear system, that book is very helpful. Okay, and k infinity is required whenever we are talking about global stability. Okay, in continuous time system, in order to talk that if you start anywhere such that you will converge to the equilibrium point, at that time this alpha 1 alpha 2 initially that is class k, now that is converted into class infinity. Similarly, the reverse of the class k, we have another class that is called class L function. Again you can see the domain and range, so exactly same kind of treatment here for domain and range like class k function. And what is property? Now this is continuous and strictly decreasing, and as s tending towards infinity, this function ls that is also equal to 0. Now actually this class of function is very interesting, that is the combination of class k function and class L function. So class KL function that has now two argument, and with respect to first argument this is class k function, and with respect to second argument that is class L function. And one of the example you can easily able to see that as s going to increase, so this function is going to increase provided t is constant. Now you can keep s constant and you can increase t, then what happens? This is decreased to 0, and due to that reason this is called class KL function. If you have any system like x dot equal to axt, obviously this is continuous time system, and if you solve it, it is not difficult to show that exactly same class of function that comes into picture. Okay, here you can see that if you this is not dot because I am solving this. So basically if you take the norm here, so now automatically xt0, so norm of this, and exponential is always positive, and if you take the norm, then what you can do, you can take a smallest eigenvalue from here, lambda t minus t0, like this. So that is always bounded by this. So now this is nothing but some kind of class KL function. Here this is class st0, that is you can just replace by st0 and e power t, you can lambda t minus t0. So in this way these class of function is frequently appearing in case of linear system as well as non-linear system. This is very important class of function that is called generalized k class function. Okay, so what we have seen in case of the class k function is always increasing, but generalized k class function has not such kind of property. So basically in some region strictly increasing property, that is okay. So obviously that is somehow generalization of that, but here you can see that once alpha s1 that is greater than 0, so this relation will satisfy, but when alpha s equal to 0, in that region this will satisfy this kind of property. I will take one example, then easily you can able to understand how basically class k function and generalized k class function are different. And these class of function is very helpful whenever we are going to deal with the finite time stability. Whenever dead zone comes into picture, at that time also this is very important, and somehow this handle somehow non-strictly Lyapunov function. Okay. Now I am going to prove that if some function is defined like this and here domain is 0 to infinity, then this will represent generalized KL class function. So if you see carefully, so this is nothing but something like this. So alpha s is continuous everywhere. Now alpha 0 if you take, then I have to first check the maxima between 0 and minus 1. So obviously that is 0, so that is 0. Okay, so that will follow the property of the previous definition. This property is also follow. Okay, now s equal to greater than 1, you can see here that s equal to greater than 1, this is actually strictly increasing, but Now alpha equal to 0, this is 0 when if you put s between 0 to 1, then obviously always maxima is 0 and their square is 0, and due to that reason this become constant function. And you can see that these two properties are somehow different from the class KL function. So what we have seen that in this particular domain, that is somehow showing non-decreasing behavior. Okay. So basically whatever I have written continuous and strictly increasing, that is only true when basically this condition will not satisfy. Okay. So here if you see carefully, then everywhere that is greater than 0 means increasing, but here that is non-decreasing. What is meaning of non-decreasing? It means that will not going to decrease, but also not going to strictly increase. That is the meaning. Okay. So some correction in definition here, by strictly increasing only whenever some kind of domain, suppose that I have domain from 0 to infinity I am talking about. So some domain that is not strictly increasing, but also not decreasing. Okay. So that can somehow in that particular way this generalized KL class function is different from the class KL function. So now another important function, that is generalized KL class function. Okay, I have already told you that KL class function has several advantages, because solution of several linear and non-linear system is somehow related by class KL function. Okay, so even if I have non-autonomous system, one can able to show that some class of solution of non-autonomous system is going to belongs to this class KL function. Here class KL function has important application whenever we are dealing with the finite time stability. So what is main motivation behind finite time stability? So we have to maintain some quantity equal to 0, and after once that becomes 0 we have to maintain that throughout the time interval, and due to that reason it is possible to show that KL class function is not enough, and Professor Hong actually shown that there exists some kind of class function phi that is called generalized KL class function. And what is property of this class function? So if you fix t, then with respect to x, that is generalized K class function, and once you fix now s, then this is nothing but it is possible to show that as t tending towards t, not infinity, t tend to some finite time, then that equal to 0, and after that is going to maintain. Okay, and due to that reason these kind of function is very useful whenever we are characterizing the finite time stability. And obviously in hybrid system also and discontinuous time system also these class of function comes into picture, and these are the property that is taken from the Khalil book. So you can see that if you have some kind of class K function like alpha 1 and alpha 2, and K infinity function that is alpha 3 and alpha 4, and KL class function beta, then they will satisfy several properties, and these kind of property whenever you are going to manipulate system, that is very useful. Means alpha inverse define over 0 alpha a, so again that is class K function. Alpha 3, because alpha 1 if you see, then that is class K function. So inverse also that is going to satisfy the exactly same property. So similar kind of property. So this is property of the composition also comes into picture. Picture means composition of two class K function is still a K class function. Composition of two K infinity class function is still K infinity class function. And these property are very useful whenever you are talking about the Lyapunov stability. So now let us come to the dynamical system. So discrete time non-linear dynamical system is represented by this. Okay, and here now Z again that belongs to some set D, and D is subset of Rn, and now F map from D to D. Here how basically that is different from the continuous time system. If you see continuous time system something like this, so you can see here that if xt is the position vector, then somehow we are talking about rate of change of position vector on the left hand side of the differential equation. Okay, so physical interpretation is totally different. Xt is position, then at that time x dot is velocity. Okay, but if you see here for discrete time system, then physical formulation wise that is very much consistent. It means that if zk is the position vector, then somehow we are assuming that zk plus 1 next instant I am talking about, so that is going to maintain their physical interpretation. Okay, so in that particular way somehow these two systems are different. Okay, now there are several examples. So this example is nothing but linear system. Non-linear system means non-linearity comes into picture. Now same like continuous time system, one can able to characterize the notion of stability of the discrete time system by doing solution of this. Okay, so one of the important stability that is called Lyapunov stability, one can able to extend for the discrete time system also. So definition is exactly same like the continuous. So whenever I have this kind of system, so interpretation is exactly same like the continuous, that I am going to give the initial condition z0 and after that I am going to generate somehow the next instant zk. So I have to solve this particular equation, and after solution, now what I have to do, I have to select some kind of ball that is related to output side, and after that corresponding to that ball there exists some kind of ball of initial condition that is depending on the epsilon, and due to that reason for every epsilon there exists a delta such that if you start from the epsilon ball you are going to live inside the delta ball. So this is zk and this is the z0. Okay, so exactly same way we can able to define, this is the notion of norm. Okay, and obviously you can able to see that this is nothing but this is Lyapunov stable. So now it is your task to prove that this is Lyapunov stable. So what is idea? Solution idea is very simple. You can substitute zk equal to 0, then you will get something like 0.5 z0. Now you can substitute next instant, so that become 0.5 and z1, and z1 you know. So basically this becomes 0.5 square z0. So in this way basically if you come to zk, so zk, that is the solution, that is nothing but power k and z0. Since this lie between 0 to 1, you can easily able to show that this is going to converge. Okay, where that is going to converge, so as k tending towards infinity, that is going to converge to the 0. Okay, similarly you can able to show here, obviously here coefficient is 1, so you are not going to converge to 0, but always you are going to remain the bounded, and somehow boundedness is coming from the definition. Now another stability concept is asymptotic stability, and here somehow apart from the boundedness I am also going to add the convergence. Okay, so same like the continuous time system, we are telling that if this k is tending towards infinity, then zk equal to 0, and somehow this is asymptotically stable. Why asymptotically stable? We have already seen that as k tending towards infinity, that is tending towards 0, and it is also possible to show this is locally asymptotically stable. So how to prove this is locally asymptotically stable? Again I have to prove that z0 there exists some kind of finite region where I can able to do epsilon delta formulation such that if I start from the epsilon ball I am going to remain in delta ball, and proof is very easy. Since I am assuming zk belongs to R, so you can take absolute value, and it is possible to show that if you bound this side, okay, so if I maintain 1 minus zk square less than equal to 1, then obviously this system, comparison system, that is looks like some kind of now differential, now we have difference inequality, and it is possible to show that as k tending towards infinity this equal to 0, and here lambda lie between 0 to 1, then only this is true, and in this way I can able to tell that this particular, from this I can able to make some kind of condition on that. So this is always a square root of 1 by 2. So if zk lie in this domain, then only I can able to talk about this kind of convergence, and due to that reason this particular difference equation is only locally asymptotically stable. And now next is called geometrically stable. So in case of continuous time system, we are talking about exponential stability. Here we are talking about geometrical stability. Okay, and in this case there exists a beta k such that that will follow this. So now it is your turn to check these two are geometrically stable. Now another very good idea, that is called finite time stability. So zero solution is called finite time stable if there exists a neighborhood n and settling time function. Okay, so same like in case of continuous time, we are talking about there exists a time that is function of the initial condition. So here I am telling that there exists some kind of function that is called settling function, such that as the next instant comes into picture, so all subsequent instant I can able to maintain zk equal to 0. Okay, and again this should be Lyapunov stable. So it is possible to show that if zk plus 1 equal to 0, so in all next subsequent step that is going to maintain that equal to 0. So it is very easy to prove. So you can see that if I will put here k equal to 0, then z1 equal to 0. So in this way z2 also equal to 0 and zk also equal to 0. So in one step that becomes 0, and after that that is going to maintain. Similarly, it is possible to show that this is nothing but finite time stable. So you can see that how to prove that. Saturation function is defined like this. So x greater than 1, that is acts like the signum function, and when that will lie between -1 to 1, then that is looks like the linear function. So as z0 is greater than 1, so what happens that if this is greater than 1, so whole value is 1. It means that within one step I can able to lie in this particular region. Now once I am in this region, we know the definition is looks like this. So basically our system now looks like this, and it is possible to show now that I can able to converge to 0 at max in this number of step, and here this function is called the ceiling function. Okay, so ceiling function means suppose you have 0.5, then that is equal to 1. So obviously a finite number of integer only is required to show the time of convergence in case of the discrete time system. And this is the Lyapunov theory, that suppose there exists a Lyapunov function, and if Lyapunov function will satisfy this kind of condition, and here some kind of operator, minimum operator comes into picture, it is possible to show that if this kind of condition will satisfy, I will discuss this thing again whenever I will come to the third lecture of this particular module. At that time I am talking about sliding mode control based on the minima, and this equation will actually play a very important role. And what is basic idea? You can see here L is some kind of constant. So delta Vk is nothing but Vk plus 1 minus Vk, that is the delta Vk, and this is the minimum of the Vk and L. So you can start with any initial condition, so and select the minima. So initially if minima is actually L, so in L slowly I am going to decay, and once it might possible that suppose that if I am starting with 5.7 is the initial condition, and each step L is 1, so next step I will come to 4.7, 3.7, and finally 7 comes into picture, and at that time Vk is 0.7 and minima if you compare, then this is 1, this is 0.7, so that is become 0.7 minus 0.7. In this way in finite time I can able to converge to the equilibrium point. Okay, and time of convergence also again you can able to give by the ceiling function. Okay, so this is the example. Similarly, it is possible to show that in case of continuous time system I have two different kind of algorithm, x dot equal to minus k signum x. So this is nothing but their variant, and another algorithm we have seen, then that is nothing but x power alpha is half signum x, or alpha here also you can easily able to take. So that variant in the discrete time system is given by this, and time of convergence is given like this. Okay, and now this is very important class where disturbance also comes into picture. So here nu is represent the disturbance. Okay, and that disturbance we are assuming that is bounded. So this external, in case of external disturbance, and again our equilibrium point is 0 0. So at equilibrium, suppose physical interpretation is that at equilibrium point we don't have any disturbance, it is possible to show that this class of system is input to state stable. So we are going to show with some example also, and definition also I am going to give. So what is meaning of finite time input to state stable? So we are telling that some system is finite input to state stable. So in absence of disturbance, so gamma function whatever we have taken, so V is 0. So in absence of disturbance, this is class KL function. What is property of generalized class KL function? Because KL class function is not enough, I need generalized KL class function, because in finite number of step I have to converge, and after that we have to maintain it. Okay, and after that this function is actually K infinity class function. So in this way, basically whenever uncertainty comes into picture, then one can able to show that finite time controller is robust with in presence of the external uncertainty and disturbance. Okay, so one example I have taken. So up to here we have already proved that it finite time stable. Now I have added some kind of bounded noise. Okay, and in presence of bounded noise, it is possible to show that once Vk equal to 0, then obviously finite time convergence. But when Vk not equal to 0, so due to the behavior of saturation function, again that will actually converge to minus Vk plus Vk. Okay, if Vk is not present, then I will converge from minus 1 to 1. Okay, now using Lyapunov function, obviously this Lyapunov function is K infinity class function, and worst case analysis here Taylor, due to Taylor series expansion, this term comes into picture, and it is possible to show now by the analysis that this is the obviously ceiling function, and if I have minimum number of step that is given by this, obviously this is function of the magnitude of the disturbance. We are assuming that disturbance is bounded by some magnitude, that is the infinity norm or some norm you can take. Okay, so as at that time it is possible to show now differential equation is converted like zk minus z0 and 1 minus vk due to the consequence of this particular equation. And now if you further analyze it, then it is possible to show that there exists some kind of time, then I will always remains the bounded. In this way you can able to show the finite time input to state stable. And again one can also able to extend the same kind of concept even if that will satisfy this kind of condition. I have already discussed here that there are two different kind of formulation whenever we are talking about finite time stability. So first formulation is coming from here, so that is minimum operator. Again second formulation is coming due to the variant of this. So with help of that also again we are able to define the finite time input to state stable, and in this way we can able to establish that finite time stable system, discrete finite time stable system is robust with respect to certain class of perturbation. Okay, now it is time to conclude this lecture. So I have discussed the finite time stability, and after that we have also seen that how one can able to maintain finite time stability in case of the disturbance, and obviously input to state stability concept comes into picture in that particular case. And we have established the Lyapunov condition for finite time stability, and we have taken several nonlinear system to demonstrate the example of the finite time stable linear or nonlinear system. So basically we have unified the approach of the continuous time system for the discrete time, and we have also seen the ISS whenever input to state stability concept comes into picture. So somehow that is equivalent to linear system, that we know that if linear system is stable, then bounded input will give us the bounded output. In case of the nonlinear system, there are some class of nonlinear system only. We have very limited class of nonlinear system, continuous or discrete. If we apply the bounded input, then I will get bounded output. So that class of system is called input to state stable system. Okay, so if our system will satisfy that kind of property, then easily we can able to design sliding mode control, and it is possible to show that in finite time I will converge to some manifold, and after that we can able to maintain. And obviously this will provide the robustness tool, and this kind of theory is very useful whenever we are talking about the non-smooth class of system. So with this primary background, in next class I am going to talk about discrete sliding mode control. Thank you very much.